I'm sure.
Okay, well, I guess the first thing is actually to thank you, Ricardo, for this invitation.
Let me introduce you formally.
Okay, all right.
So we're getting started, and everybody, thanks for coming here and via Zoom. And it's a pleasure to welcome our colleague, and I would say friend. We've been interacting for a number of years right now, Sasha Rakovic, who is currently a full professor at Beijing Institute of Technology. And many of you know him for some of his pioneer work on model predictive control, tube MPC, and many of the things that he's going to show us today. He received a PhD in control theory from Imperial College London. His research was awarded the Earl Cadwalader Davis Prize in 2005 as the best PhD thesis in the Department of EEE, I guess it's electrical engineering, maybe electronics as well, at Imperial College. And he's been highly cited. He has more than 120 papers with more than 8,000 citations, according to Google Scholar. And these articles have been published in internationally recognized journals and conference proceedings. His interest, and we're going to see much of this today, is driven by mathematical problems that are in the intersection of AI, control, dynamics, systems, and optimization. With that being said, Sasha, it's a pleasure to have you here. Thanks for joining very late in your time zone. So much appreciated.
Well, thank you, Ricardo. So I guess now I can say that I really appreciate your invitation, and I would also like to thank you for a number of interactions we had over a period, and for your contribution to the activity I have in Beijing to the Chinese Model Predictive Control School. And I hope that actually we'll continue with interactions, and hopefully we'll find more of intersection of our research interests and maybe do even some joint work. Now, I guess my work was mostly on model predictive control, but during my PhD, my work really revolved about the questions of robustness of model predictive control. But it was really concerned with the uncertainty, which wasn't really stochastic, but it was a set membership type of uncertainty, which essentially meant you dealt with the problems in which you don't have any probabilistic information about uncertainty, but rather you have bounds. And then you're looking at a kind of robust formulations. And during that period, we introduced a technique which is now recognized as a tube model predictive control, and which has become, well, extremely useful. It's being used in reinforcement learning. It's been used within safety controls all over the place, really. So it is definitely one of the more useful techniques in robust model predictive control. And perhaps I should not have said that, but essentially you can Google it, and you can even Google will confirm that actually it has been used extensively. I'm not saying Google is the most credible source for the academic research and impact, but essentially it will give you the numbers, and the numbers shouldn't lie, as somebody said. So now today's talk is actually something which at the time when I started was perhaps offbeat, and it's still slightly off the main research lines in modern research lines in control, which seem to revolve about reinforcement learning and, well, interaction of artificial intelligence within the controls and dynamics. But in a way, I think it's an important line of research because it touches upon the basic fields of dynamics and controls and convex geometry. And the title essentially, well, it's in a way hints what the talk is going to be about. So the title is Minkowski, Lyapunov, and Bellman, Inequalities and Equations for Stability and Optimal Control. So in a way, what I would like to do is I would like to combine the concepts and notions and, if you will, research of three people, which is Hermann Minkowski, well known for many things, but also contributor to fundamental concepts in convex geometry, Alexander Lyapunov, of course, stability theory, and Richard Bellman, optimal control. And what's the punchline of this talk? Well, the punchline is I'm looking for a systematically fundamental alternative to linear quadratic mean in controls and dynamics. And of course, as with any piece of work you try to develop over a period of time, you interact with some people and you should give credits. And I'm I would like to acknowledge actually contributions in various forms by Professor Zvi Einstein, in particular for constructive feedback of numerous occasions, and also to Rafael Gobel for very helpful initial discussions when I commenced on actually conducting this research. So now, outline of the talk, I'll have to give you very few definitions from the convex geometry, or what I call Minkowski algebra of convex bodies. And then I'll have to introduce the notions that actually form the core of the talk. So the first concept is Minkowski-Lyapunov inequality and equation. The second one is the control Minkowski-Lyapunov inequality. And then the third one is Minkowski-Lyapunov-Bellman inequality and equation. Obviously, by the fact that I'm using the terms Minkowski-Lyapunov and control Lyapunov or Lyapunov-Bellman, it's clear that actually the underlying themes are stability and optimal control. And the fact that I'm using Minkowski indicates that actually I'll be dealing with Minkowski functions within the stability analysis and optimal control synthesis. So let us start with the basics. Now, in principle, underlying object will be a proper C set. Now, what is a proper C set? Underlying space is a finite dimensional, so Rn, and the proper C set is a convex compact subset which contains the origin in interior. An example of a set is shown here, and this set, you can think of this set as being composed from the unions of two norm balls, one norm ball and infinity norm ball, by taking the parts of these norm balls in the quadrants. And the picture on the right shows the Minkowski function. Now, the Minkowski function is essentially an interesting function. It's also known as the gauge function, and it's given as a minimum of eta, x element eta s, and eta being positive. So effectively, it means if you have a point x, you look at the ray from 0 to x, and you scale or contract the set until the point is contained in the set. Typically, the point will be on the boundary. Now, if you look at this function, this is a kind of form of the function associated with this shape. So what you can see that this function actually has a lot of nice properties when you deal with proper C sets, which is a regular setting. In this case, essentially, this function will be continuous and sublinear. Now, what do I mean by sublinear? Sublinear, it means it's positively homogeneous of the first degree and subadditive. And actually, this function will be zero only at 0, and it will be positive away from the origin, and it will be finite. Now, however, what you can see actually, even for this reasonably simple shape, the function actually fails to be differentiable. So essentially, those corners in the sets actually transform in points of non-differentiability of the function. So typically, you see that actually, even though the function has a lot of nice properties, it's not differentiable. Now, why one should bother with Minkowski functions? Well, when you deal with Rn, any vector norm on Rn is generated by the Minkowski function of a set which is symmetric with respect to the 0. And the closed unit norm ball is the set S. And in particular, the norms that actually everybody is familiar, little L1, little L2, little L infinity, are particular cases where actually infinity norm, well, the infinity norm ball is a square, for two norm ball is essentially a circle, or the sphere in higher dimensions, and actually you have a diamond or hyperdiamond for L1. Now, these are very special cases. So, in fact, it is a statement, and it's a result that any vector norm on Rn is generated by the Minkowski function of a proper C set. So the Minkowski functions encapsulate the vector's norm. So therefore, it's quite natural to look at these functions. An equally important function, which actually goes hand in hand with Minkowski function, is a support function. Now, why support function? What is support function? Why bother with the support function? Actually, well, if you look at the points on a unit sphere and say direction 1, direction 2, direction 3, up to direction 6, what the support function will give you, it will give you maximum in a specific direction over the set that you consider. Now, if you consider this particular set, if you maximize it in direction 1, what you're going to get, if you look at the value of support function in that particular direction, that will allow you to define supporting hyperplane to the set. And actually, if you run through all points, you'll get different supporting hyperplanes, so therefore you get a description of the set. So you can see that the set is the same as in the previous graph, but you can see the support function is a kind of rotated for 180 degrees. And I'll come to the relation of support and Minkowski functions. But for the time being, let me just define support function. So the support function is defined for a non-empty closed convex set in Rn, and it's given as the supremum in a particular direction over the set S. Okay. Now, of course, when the set is compact, then essentially supremum is maximum. Now, the main reason why one would like to look at the support function is the fundamental correspondence between the convex, non-empty compact convex sets in Rn and support functions. In particular, what is the Essentially, this is a deep result that can be found in the book by Schneider and Rockefeller. It says if S is a non-empty compact convex set in Rn, its support function is a sublinear function. And conversely, if F is a sublinear function, here F maps Rn to R, then there is a unique non-empty compact convex set S in Rn with the support function of F. So therefore, support function essentially gives you one-to-one correspondence between the functions and sets. Now, this correspondence has a lot of implications, and the most important of which are that actually you can convert certain relations between the sets to the relation between the functions. And in particular, the following are the properties that actually will play a role in the development of the results. If you take any non-empty closed convex sets S, S1, and S2 in Rn, and any matrix M in Rp times N, then we can say the following. S1 is subset of S2 if and only if support function associated with the set S1 is less or equal than support function associated with the set S2. Now, this tells you that actually looking at the set inclusion is the same as looking at the functional inequality. The second thing that matters is actually if you look at the Minkowski addition of the sets S1, S2, where the Minkowski addition is merely just the sum of all vectors from the sets S1 and S2, then that's equal to the sum of the support function. Now, this is of the support functions with respect to the set S1 and set S2. Now, this is an important property because it tells you that actually you don't really have to perform geometric sum of the sets. You can actually move this to the addition of the functions. And sometimes this may be easier than actually performing geometric operations on the sets. And finally, what you also want to observe is that actually if you look at the support function over linear transformation of a set, then this is the same as the support function over appropriately linearly transformed direction. So essentially you just take M transpose Y because we are dealing with the reals here. Now, these are three basic properties which, however, will play a role. These properties, even though they're very direct, they also have implications in terms of the computational geometry that people employ in the geometric approaches to the control. Specifically, I would like to point out that actually these two properties enable one to look at the reachability through actually propagation of the support functions rather than propagation of the sets. Now, okay, so but why bother with support and Minkowski functions? Actually, because they're essentially polar to each other. Now, to explain that, we all know that actually L1 and L infinity are dual norms. L2 is self-dual, of course, L infinity and L1, and the shape I've given you has a polar shape, okay, and vice versa. Now, this notion actually hangs from the notion of a polar set. The polar set for a set S with 0 in Rn is given as a set of all points such that Y transpose X less or equal than 1 for all points in the set S that you consider. Now, this is an interesting notion. It's related to the duality in principle, and this notion has very nice properties when you look at the regular sets. Essentially, what it tells you if you look at the property set S, then its polar set is also property set. And actually, if you perform polarity operation once again, which essentially means if you look at the bipolar set, then you get the set you started from. So in other words, polar of a property set is a property set itself, and actually if you look at the bipolar of a set property set, it's the set itself. Now, as I said, the link between Minkowski and support function lies precisely from this polarity and lies in the fact that Minkowski function of a property set is equal to the support function of the polar set. Okay, now that means for all x in Rn, gauge of Sx is equal h of S star x. So I would like to reiterate here 4 properties which are important, which will enable me to develop some of the conclusions later on. So the first is this polarity between the Minkowski functions and the support functions, and there are these rules for actually performing the sums of the sets in terms of the sums of the functions, or actually looking at the linear transformations of the sets and support functions, and essentially looking at the inclusion, which is converted to the functional inequality of support functions. So these 4 rules will be needed to develop the things that I want to develop. Okay, if you excuse me for a second. So now, in terms of the Minkowski-Lyapunov inequality, so several years ago, I had a colleague who came and presented the work on polyhedral Lyapunov functions. At the time, I was a visiting scholar or visiting researcher academic in Oxford, and the talk was on polyhedral Lyapunov functions. And I had a very simple question. So if you're able to solve the Lyapunov inequality with polyhedral functions, can you actually solve the Lyapunov equality or Lyapunov equation over such class of functions? And of course, this friend has attempted, but solution couldn't be found because essentially it's not necessarily true that actually when you look at inequality that actually you get solution to be polyhedral. So the point was that actually over the time, I realized that essentially Lyapunov equation over Minkowski functions was actually dual to an object that I was very familiar with, which is actually the minimal robust positive invariant set. And this has initiated my interest in my research. And then actually there was a sequence of the paper starting from 2014. And I'll share the slides so you can actually look through all of these. Now I'll just extract the main points of these developments. So the first question is a very simple question. We look at the linear dynamics. We have a decrease function, which is Minkowski function of a property set Q. Set Q is given, matrix A is given. What we want to know if we can solve the Lyapunov inequality, which is just essentially V of AX plus L of X less or equal than V of X. And we want to solve this inequality over the space of Minkowski functions. So we look for a function V of X to be gauge of P of X, where P is a proper C set. Now, if we summarize this, what we really get is that essentially gauge of PAX plus gauge of QX less or equal than gauge of P of X. So this is purely Lyapunov inequality over the space of Minkowski functions. Nothing is that. Now, interestingly enough, I kind of struggled to find results that actually would enable me to claim the solution to this. And in either case, because of that, I developed a bit of theory. Now, as I said, we start from this Minkowski-Lyapunov inequality, and we utilize these operations and properties between Minkowski and support functions. So the first step is that actually you perform the polarity operation. So you replace Minkowski functions with the support functions. So essentially, instead of gauge of P of AX, you have a HP star AX. Instead of gauge QX, you have HQ star X, etc. And instead of gauge P of X, you have HP star of X. Then you do linear transformation, which means matrix A goes into transpose in front of the set P. Then you sum up those two support functions and you get a single expression. Now, essentially what we are doing now, we are comparing two support functions. Comparing two support functions essentially tells me that I am dealing with a set inclusion. So essentially that means this set has to be less or equal than this set. So essentially we started from Minkowski-Lyapunov inequality, which is functional inequality, and this inequality will be satisfied if and only if this set inclusion holds true. So this is a characterization of all Minkowski functions which verify Lyapunov inequality. Now, of course, at this stage, when you recognize this comparison of the the support functions, you can apply polarity operation once again, and you can express this in terms of the Minkowski functions. So you can take a polar of this, that gives you G of P. And now when you're comparing the gauge functions or Minkowski functions, then inclusion is reversed. But that conclusion follows even from this set inclusion, because essentially, if I compare two proper C sets, and if I take polars, the polars will satisfy the reverse set inclusion. Okay, now this gives me what I call fundamental property of the Minkowski-Lyapunov function. So to sum it up, the Minkowski-Lyapunov inequality is just a Lyapunov inequality over the space of Minkowski functions. This inequality is equivalent to the set inclusion, which is A transpose P star plus Q star subset equal than P star. And of course, we also have a polar form. So therefore, this characterizes all Minkowski-Lyapunov functions. So the statement is the following. If you take any proper C set Q and any matrix A, Minkowski function X to gauge of P of X of a proper C set P in Rn verifies Minkowski-Lyapunov inequality if and only if polar sets satisfy this set inclusion, or if and only if P satisfies this inclusion. Now there are two forms. It depends on the description or representation of the set you deal with. One or the other might be more convenient to utilize for computational purposes. Now, but when can we say the solution exists? Well, actually, the solution will exist if and only if A is strictly stable. Clearly, if we can solve the inequality, then we know A is strictly stable. But the fact that Q is actually proper C set, this means that A transpose contracts over the whole space. So essentially, that means all eigenvalues of A have to be strictly inside of the unit disk. So spectral radius of A has to be less than 1. Now, okay, but what can we say about this set inclusion? Because this is a peculiar set inclusion, because essentially what it says we take a set, we perform linear transformation, we add another set, and we remain within the set. Surely this is a property that has to be characterized. And this property is nothing else than actually robust positive invariance property. Let me make this more concrete. So we started from the nominal dynamics, had a Minkowski decreased cost function, where the set Q was a proper C set. And then if we formulate slightly unusual polar dynamics in which we're going to take transpose of A and we add disturbance, the disturbance now actually takes the value in the polar set of the set Q, then we have a perturbed linear dynamics. But then actually notion that is of interest is robust positive invariance. So essentially we can say that set Z is a robust positive invariant for these dynamics with respect to this uncertainty if and only if A transpose Z plus W is subset of Z. So that means for any point inside of the Z, when I start and I run it through the dynamics, no matter what disturbance happens, I remain inside of the set. But now if I look at this inclusion, A transpose Z plus W is subset or equals Z, given that W is a Q star, and if I put Z equal P star, I'm obtaining precisely this equivalent set inclusion. So that essentially means that the stability analysis through this Minkowski-Lyapunov inequality gives me an analysis of robust positive invariance in terms of regular proper C sets for the perturbed dynamics. And therefore, I can make a following statement. Minkowski-Lyapunov inequality of this form. So for all x in Rn, gauge of P of Ax plus gauge of Qx less or equal than gauge of P of x. And we have this equivalent set inclusion A transpose P star plus Q star subset equal to P star. So if you take any proper C set Q and any matrix A, now the Minkowski function of proper C set P in Rn verifies Minkowski-Lyapunov inequality even only if the polar set P star of the set P is a robust positive invariant set for these dynamics. Z plus equals A transpose Z plus W, where W actually is a polar of the set Q. Now, perhaps at this point in time, I should add something that I haven't said. So I have intentionally actually taken the set Q to be a proper C set. Now, this proper C set essentially means that I am looking at the most regular case, which essentially means that A is strictly stable. Of course, we can have a case when A is marginally stable, but then we have to actually decompose the state space. That essentially would be a distraction which would remove the elegance of the conceptual aspects, if you will. For that reason, I have actually looked at the pure or a clean setting in which actually I work with the proper C sets and the strictly stable matrices. The rest is just essentially algebraic decompositions, so it doesn't really add much apart from the tedious algebra. Now, let us look at the equation. So now so the first thing is, of course, you have a lot of functions or a lot of spaces of functions in which you can solve the Lyapunov inequality. But then the question is actually, can you solve the Lyapunov equations in these spaces? And this is the second question I want to answer. So in this case, I want to solve equality. But actually, if you recall, so it is the same setting. X plus is Ax is nominal dynamics, A is known, we have a decrease, Q is a proper C set which is given. We want to solve Lyapunov equation, where actually the function V of x is now a Minkowski function of the set P, induced by the proper set P. And the set P is unknown. We want to see actually if there is such a set P that actually it verifies this with equation. Okay, so, but if you remember when we performed this operation, so all what we did, we replaced gauges by the support functions, and this was equal. So essentially, the relation was not affected in any of our steps. So in other words, we can repeat everything that was done for inequality. So I can replace gauges by the supports of the polar sets. I can perform this linear transformation because that essentially just equates those two support functions. I can sum up those two support functions because that's the same function. And now I'm comparing two support functions, and it's not anymore less or equal, but now I have equality, which means it's less or equal on both sides, which means essentially I have inclusion on both sides, which essentially means I have a set equation. So in other words, to solve the Minkowski-Lyapunov equation, the polar of the set P has to solve this equation, set equation. And this set equation is nothing else than the fixed point set equation, where actually you look at the map X to A transpose P plus Q star, okay? And this map now works on the space of sets. And of course, you can take a polar of this equation, and since the sets are equal, their polars are equal because the sets are proper C sets. Now, coming back to summarize this, essentially what we can say, we can solve the Minkowski-Lyapunov equation or the Lyapunov equation over the space of Minkowski functions if and only if we can, the set P star is actually the polar of the set P satisfies this set equation, or it satisfies this. So if you take any proper C set Q and any matrix A, Minkowski function X to G P of X of proper C set P verifies the Minkowski-Lyapunov equation if and only if the polar set P star of the P verifies the set equation A transpose P star plus Q star equals P star, or equivalently if and only if set P verifies this. Again, you can look at two forms of this equation, because depending on the representation which you want to employ for computations, one or the other might give you certain advantages in terms of the numerics. Now, when can we solve this? We can again solve it if and only if A is strictly stable. And now actually what happens when A is strictly stable, this essentially, if you think of this as a map, if you think about the map X to A transpose X plus Q star, where X is a set, because essentially Q star is a full dimensional and A is a strictly stable, this map will be actually contraction. Now, because it's a contraction, that essentially means you can invoke the Banach contraction theorem or Banach contraction principle, Banach fixed point theorem, to claim that actually solution is unique. So now that essentially means not only that actually there exists a solution to the Minkowski-Lyapunov equation, but actually solution is unique. And this is very nice. And this matches everything that's known for the quadratic case. Now, let us actually give interpretation that comes from the polarity. Now, again, recall that actually we had this nominal system, we formed this perturbed system with disturbances, where disturbance was defined through actually polarity operation. And now we need to define the notion of the minimal robust positive invariant set. Now, a set Z is the minimal robust positive invariant set for this perturbed dynamics, if and only if it is a robust positive invariant set, and it is minimal with respect to the set inclusion over all. Now, there is a technical point, non-empty closed robust positive invariant sets for the perturbed dynamics. Now, essentially, the reason why you want to look over non-empty closed sets is actually if the sets are not closed, essentially it becomes very difficult to compare the sets. And typically you want to take limits of the sequences that are generated in uncertainty, so therefore you still want to have a kind of notion of convergence, and therefore you need to have a closeness of the sets to which trajectories converge ultimately. So that's the minimal, and actually because the minimal robust positive invariant set is a character, is a solution to this fixed point equation, there is a link. So essentially what it says the Minkowski function x to gp of x of proper C set verifies the Minkowski-Lyapunov equation if and only if polar set P star of P is the minimal robust positive invariant set for this polar perturbed dynamics. And this is a very nice interpretation. Now, of course, I can summarize this. What can I actually conclude based on these results? I can conclude two things. In terms of kind of theoretical considerations, I can say the stability analysis via Minkowski-Lyapunov functions of the linear dynamics is essentially identical to the robust positive invariance analysis of the perturbed dynamics for proper C sets. Okay. Now, that's an interesting thing because essentially it tells me, okay, if I understand either of the problems, I should be able to solve the other problem just using duality. Now, I'll come back to this actually, because this might be a bit misleading, because of course you can do stability analysis of linear dynamics using quadratic functions, but there is a different point I want to make. So let me go back to the computational ramification. Now, what actually matters here in computational terms, it says the following. If you compute Lyapunov functions in the space of Minkowski functions, that is the same modulo polarity operation actually computing the robust positive invariant sets. So that essentially means either I can compute both Minkowski-Lyapunov functions over the space of Minkowski functions and proper C sets which are robust positively invariant, or I can't compute any. So, and in fact, actually it turns out you can compute both. So essentially this is a nice result that actually you can link to the duality generators of these Minkowski-Lyapunov functions and the robust positively invariant sets of the polar dynamics, or vice versa. So you can use the methods from different fields to actually, well, they're not quite different fields, but essentially this link has not been made, at least in some of the literature. Not, I mean, it's very difficult to make claims for general literature, but in the literature, in the fields where I operated, this was not unobserved, let's put it that way. So this is an interesting observation. Now, but let me come back to the point here. So the point is, of course, you're going to tell me, look, all what you're telling us is a kind of cheat, because essentially, why bother? You can do linear, I mean, it's a linear dynamics. You know that you can solve quadratic inequality or quadratic equation, and you can get very nice quadratic function to verify all of these properties. Okay, well, you can do that, but still you don't have this interpretation of the robust positive invariance and duality. But actually, more importantly, well, if you want to look at the quadratic functions, what happens if you allow perturbations or uncertainty in the matrix A? So now, if you look at the robust case, actually you can't solve, I mean, you can look at the robust stability when you have uncertain matrix A, or when you have a polytoporous, let's say convex hull of matrices A, or a compact set of matrices A, you can actually then, well, quadratics will give you only sufficient conditions for stability, and such sufficient conditions can be terrible. Actually, there are very simple examples which show that actually quadratics fail to verify asymptotic stability of very simple dynamics, even in 2 dimensions. Now, why that happens? It happens for one fundamental reason. When you actually look at the robust case, you need to take a max operation, and taking max operation, essentially max of quadratics is not necessarily quadratic, and you can't bound it, you can't essentially find the nice bounds to quadratics. So even though you have linear matrix inequalities, this is only conservative sufficient methodology. On the other hand, if I look at the robust Minkowski-Lyapunov inequality, actually I can do two things in the case when actually I allow matrix A to be uncertain. As long as A belongs to, say, actually I developed results for A belonging to a convex hull of finitely many matrices, then actually you can solve both inequality and equation, and you get necessary and sufficient conditions for stability of such linear inclusions. Now, the reason why this happens actually comes from topological consideration, which tells you that the maximum of the Minkowski functions is a Minkowski function. Now, in other words, the Minkowski functions are closed under the operation of the maximum, and therefore there is no any conversation. There is no any conservatism in a kind of approximating the max, which you would have to do if you deal with the quadratics or some other forms of the functions. Now, in fact, actually, you would have a problem very likely with most of the smooth functions, because when you take a max of the smooth functions, that fails to be smooth in general. Okay. So on the other hand, Minkowski functions being non-smooth actually are closed under max operation, and that's their utility. Now, there are two things that have been developed. The inequality in the robust setting has been addressed in Automatica, and the equation was addressed in IEEE paper. And to support the theory, there is a recent publication on a kind of computations in the polyhedral setting, and this is also published in IEEE. Okay, so this is a kind of very simple setting. It provides essentially very nice, in my opinion, very nice observations. I mean, and this is, of course, questionable because the beauty is in the eye of the beholder. So the point being here is that while actually what I presented is presented for the simplest case, there are extensions to the complicated case, or, well, again, this is, it's a matter for discussion whether the inclusions are more complicated than the difference equations, but essentially in terms of the necessary and sufficient conditions, this is definitely a plus. And therefore, this offers non-conservative tool compared to the quadratic function, and this is one of the advantages. Now, another point that actually matters is actually what happens if you get a bit more ambitious, and when you look at the control case, so now you have a control system and you actually want to add a control parameter. And now actually what the question becomes, you have a linear system, AX plus BU, X plus, this is all discrete time, and the matrices are known. You have a stage cost function, gauge of C of XU. Now it's given through a set C, which is a proper C set in Rn plus M. And now you ask yourself for a Minkowski control Lyapunov function. Now, what would be this? This would be a control Lyapunov inequality in terms of the Minkowski functions. So essentially, for all x in Rn, you want to find the u in Rn such that gauge of P of Ax plus Bu plus gauge of C of Xu is less or equal than gauge of P of X. So effectively, this is a very simple question. Again, take a control Lyapunov inequality and try to solve it over the space of Minkowski functions. Now, this can be worked out, and one of the reasons that this can be worked out and you can get very nice results, and this is kind of very interesting, because it was another kind of one of these which was not so easy to find in the literature, at least not in the form that I presented. So in order to handle this, actually, you need to simplify the function on the left-hand side. Once you simplify the function on the left-hand side, you'll handle this essentially quantifiers. We have a for all x, there exists a u. So this will tell you essentially sup-inf, so to speak. But essentially, in order to handle that, we need to handle this functional inequality first. And if you look at this left-hand side, well, we can actually perform this. I gave you 3 or 4 rules. I gave you 4 rules, and these 4 rules actually do the whole heavy lifting in this analysis. So essentially, you start from the gauges or Minkowski functions PAX plus BU gauge C of XU. You convert this to the support functions using polars. Then you actually, now, of course, AX plus BU is AB times XU. So you can actually do AB transpose P star. Now, you can sum up those 2 support functions. And then you can do polarity, and you can get gauge of Minkowski function. So therefore, the sum of these gauge functions, so Minkowski function, is a Minkowski function itself. Now let us analyze what is the Minkowski function of. So this set R is equal AB transpose P star plus C star and everything star. Now, what we know the C is a proper C set. Therefore, its polar is proper C set. We know P is a proper C set in Rn. So P star is a proper C set in Rn. Therefore, linear transformation of a proper C set in Rn is a proper C set, is guaranteed to be a C set in Rn plus M. But now we have a sum of a C set in a proper C set, that's going to be a proper C set. And if you take a polar of a proper C set, we get a proper C set. So that means this sum is a regular Minkowski function. And that simplifies things a lot. So you can summarize this. This holds for any P, any A, B, and any C. If you take any property sets P and C in Rn and Rn plus M and any matrix pair A, B, then actually this sum is equal to this gauge function. So for all X and U in Rn times M, gauge of PAX plus BU plus gauge of CXU is gauge of RXU, where R is a property set given by this expression. Now, this simplifies your control Minkowski-Lyapunov inequality considerably, because now we're just comparing two Minkowski functions through, and we have these quantifiers. Now, what does this mean? Essentially, in principle, it means if I pick an X, I should be able, now, if I pick an X, that's going to give me value of the gauge of P of X. But then essentially to satisfy this inequality, it means I have to find a U such that XU is inside of this set. Okay. Now, this essentially tells me that set P has to be inside of the projection XU to X of the set R. And this is the fundamental property of all control Minkowski-Lyapunov functions. So I can state the following thing. Let me summarize it. So control Minkowski-Lyapunov inequality for all X in Rn, there exists a U in Rn such that Lyapunov inequality, control Lyapunov inequality over the space of Minkowski function holds true if and only if P is a subset projection from XU to X of the set R, where set R is given by this. Okay, so the statement is therefore, we fix a set C, A and B are fixed, and then we look for a set P. That's what the statement is about. So if you take any property set S in Rn plus M and any matrix AB, matrix pair AB in Rn times M times Rn plus M, Minkowski function X to gauge of P of X of property set P verifies the control Minkowski-Lyapunov inequality if and only if P verifies this set inclusion. Okay, so now this is the characterization of the, essentially, which is shifted from the functional space to the space of sets. It might be useful. Now, when you talk about stabilization, and especially control stabilization, the next thing you need to discuss what is the set of controls which actually achieves the stabilization. And if you look at this Minkowski-Lyapunov inequality, we have to associate this strongly stabilizing set-valued control map. Now, essentially, what that would be set of all controls for a given X, which actually ensures satisfaction of inequality. Now, this is particularly important in terms of the simplification we achieved, because essentially, if you remember what we achieved, we converted this control Minkowski-Lyapunov inequality to this very convenient form. And now, the convenient form essentially says for all X in Rn, there exists a U in Rn such that XU in G of P of X times R, and that actually gives me almost closed form of the strongly stabilizing set-valued control map. Essentially, it tells me that for all X in Rn, this strongly stabilizing set-valued control map is a set of all points U such that satisfies this membership condition. Okay, so I pick an X, I get gauge of P of X, I scale R for that value, and then actually XU has to be inside of that set. That's typically boundary of the scaling. Okay, so now, okay, so this is the equivalent form of the strongly stabilizing set valued map, and I now can discuss its properties. Okay, so if I take any property set P and C, and if the Minkowski-Lyapunov function G of P verifies control Minkowski-Lyapunov inequality, what can I say about this map? Well, I can say first it's non-empty relative to Rn. So for any point in X in Rn, there is a strongly stabilizing control. Furthermore, what I can say it's positively homogeneous of the first degree. So why it is positively homogeneous of the first degree? R is a proper C set, and gauge of P of X is sublinear, therefore it's positively homogeneous. It's actually, I can scale everything. Now, it's a compact and convex valued. What it means that it's compact and convex valued? It means for any point X, the set K of P of X is compact and convex. Now, why is that? R is a proper C set, and gauge of P of X is convex. So that will, and it's actually finite valued, because it's finite valued and R is compact, that's going to give me compact valued, because gauge of P of X is convex and R is convex, that's going to give me convex valued. It's locally bounded, again, for the same reason, because R is a proper C set, so it's compact, and gauge of P of X is finite. And finally, it's outer semi-continuous. What outer semi-continuous means, it's a graph of this set-valued map is going to be a closed set. Why it's going to be closed set? Because R is a proper C set, and gauge of P of X is essentially continuous function. Okay, so this is a very, the strongly stabilizing set-valued control map has a lot of properties. I'll exhibit some of these maps in the examples towards the end of the talk. Now, okay, so then the question arises, when can you solve this? Well, there are some ramifications. Actually, if you can solve this, essentially what it says, you can make the dynamics, closed loop dynamics contractive. So that means matrix pair AB has to be strictly stabilizable. On the other hand, if the matrix pair AB is strictly stabilizable, essentially you can find the K which strictly stabilizes the system. You can build a Minkowski-Lyapunov function. So therefore there exists a control Minkowski-Lyapunov function. So that means that essentially there exists a control Minkowski-Lyapunov function if and only if AB is strictly stabilizable. So that's what this statement says. And if you want to examine certain structures, typically people examine polyhedral structures. So if these Minkowski functions are Minkowski functions of polytopic sets, so the sets described with finitely many inequalities, affine inequalities, then actually you get a preservation of polyhedral properties, so that you actually continue dealing with the Minkowski functions of polytopic sets, and actually the set-valued map admits an explicit polyhedral form. What it means, polyhedral form? Essentially, it means it's a polytopic valued, and its graph is the finite union of polyhedral cones. Now, because of this structure, actually, in this particular case, you can say a bit more about strongly stabilized set-valued control map. Actually, you can say it's ellipsis continuous with respect to the Hausdorff distance. Okay, now, again, well, this is nice. The true power comes from the actually generalization to the uncertain matrices A and B. So actually, you can look at the robust case where actually you're taking maximum over matrices A and B in some convex set M, which is typically finite convex hull of the finitely many matrix pairs AI, BI. Then actually you can solve this, and this is worked out in details in my Automatica paper in 2021. Now, this is another point where actually, once again, you get this advantage of the Minkowski function over quadratic or essentially smooth functions. And this is typically because of the, exactly as I said, properties that actually max of the Minkowski functions is a Minkowski function. Well, actually, max of smooth functions is not necessarily smooth function. And definitely max of quadratic functions is not necessarily quadratic. And when I mean quadratic, I typically mean convex quadratic functions, because I'm talking about stability and optimality here, which is typically considered. Now, okay, so the final step is now actually you can get more ambitious, and you can actually say, now, fine, you can solve this inequality, but what happens if I want to find an optimal control U? Now, if I want to find an optimal control U, actually what you're looking for minimum over the left-hand side. Now, let us just reflect what is this left-hand side. We have a stage cost, and we have a cost to go. Now, why this is cost to go? Well, if the value function was gauge of P of X, then actually gauge of P of AX plus BU would be cost at the next point in time, at the successive state, because this is what our dynamics is. And minimization of this would be nothing else than one step of the dynamic programming. So therefore, everything now depends on characterizing the minimum of this function. We already know that the sum of these two Minkowski functions is a Minkowski function, very nice Minkowski function. And now if we manage to characterize the minimum of such Minkowski function, maybe we'll actually be able to solve the stabilization problem under optimality as well. Okay, so this is the, I guess, the ugliest slide, but I'll try to explain. So essentially what you're gonna do, we already know what the set are from the previous considerations. So that was AB transpose P star plus C star and everything star. So that was a proper C set. Now let's just say it's a proper C set, and let's form S to be its projection on Rn. So that's a projection of XU to X from R. There are two things to observe. They're relatively direct. First, if I pick an X, then that X is going to be in gauge of Sx times S. And then there will be some V, because I defined this through a projection such that XV is inside of gauge of SXR. But then this means that actually minimum of gauge of RXU is going to be less or equal than gauge of SX, because V is merely feasible point. So I have this inequality. On the other hand, X in Rn, because of the definition of the projection, there is some V such that XV is inside of the minimum. Now, this comes for the following reason. Firstly, the minimum is well defined, because this function is essentially the Minkowski function of proper C set. If you remember what I said, it's a continuous, it's a sublinear, it's 0 at 0, it's a positive away from 0, and it's finite valued. In fact, actually, this function, because it represents the norm, is actually very nicely inner and outer bounded, and that's uniform with respect to each of the variables you fix. So that's very nice. So the minimization is well defined. So there is a R-min set is non-empty. So therefore, that means this is satisfied. But what does that mean? Then essentially this means that X has to be, if I do a projection, then X has to be inside of the minimum of this function times S. But that tells me that the gauge of Sx has to be less or equal than minimum. So therefore, I have these two inequalities, which actually tells me that essentially to get the minimum of this Minkowski function of Rxu, what I need to do, I need to project the set S to the Rn. Okay, and this is a nice formula. It's a closed loop minimization, and then actually this simplifies my expression. So S is a projection of R onto Rn. Minimum of the gauge function with respect to U. This is a parametric function as U Rex. This is a Minkowski function of Sx. So what is the argmin? Well, argmin is a set of all points such that the objective function is less or equal than the value function. Of course, it cannot be less, it's equal, but this is just a formalism, you write it. But if we have this is precisely similar inequality we had before. That means xu is inside of gauge of Sxr. Now, I think one should observe here, we have now Minkowski of Sx. In the control case, we had a gauge of Px because we didn't look for optimality. So there is an optimality condition added here. And you can summarize this as a theorem. So if you take any property set P, any property set C, and any matrix pair, then the minimum of this function is just this Minkowski function, and argmin is given by this form. Now, what you can observe that set R is the same as before. And now you can see that S is a projection. And as I said, what you'll see now in the definition of this optimal set valued map, argmin actually, it's not gauge of P of X, but it's gauge of Sx. Now, that's kind of characterization, and now we can simplify this. So this comparison of the minimum of this function, this is minimum of R of this function, and that essentially now in terms of gauge functions is just gauge of Sx less or equal than gauge of P of X. And that essentially means P has to be subset or equal than S, because gauges reverse the inclusion of the sets. So essentially what it says that actually we characterize all Minkowski-Lyapunov-Bellman functions. So if I take any property set in Rn plus M and any matrix AB, matrix pair AB in Rn, okay, appropriate spaces, compatible dimensions, then actually Minkowski function X, gauge of P of X of property set P, verifies the Minkowski-Lyapunov-Bellman inequality, if and only if the set P verifies the set inclusion P is subset or equal than S. Okay, so now there is a ramification of this. I want you to actually, I know it's a lot of symbols and it's a lot of mathematics, but I just want you to keep in mind P subset or equal than S, because I want to make another point. Like, now this is a nice characterization. Why this matters? Now, when I look at the optimal set valued map, which is stabilizing, I have a gauge of S of X instead of gauge of P of X. Now, we have a P subset or equal than S. That means gauge of Sx is less or equal than gauge of P of X. So therefore, that means the set valued map which stabilizes with optimal action is strictly subset of the one which only stabilizes, which is quite natural. Okay, that's the point. Now, this map has the same structure as the other one, and it actually has the same property. So it's positively homogeneous of the first degree, it's non-empty relative to Rn, it's complex convex valued, locally bounded, and outer semi-continuous. So it's a very nice map. Now, when can you solve this? Again, for the same reasons, you can solve this because essentially you're adding minimization on top of the stabilization. So essentially this can happen only if and only if AB is strictly stabilizable. And because the setting is regular, the problem is well defined. Now, polyhedral structure is preserved. I'll go over that. The main point, again, the importance is that actually you can solve min-max, where actually you look for a mean over U and the max with respect to the uncertainty in AB. So essentially you can actually handle robust case under optimality. Now, that's again, thanks to the closeness of these two properties. So now, not only that actually you have a closeness of the Minkowski functions over the maximum, but also you have a over parametric minimum with respect to U. So essentially it's closer than the min max. And that's a very nice feature, but again, I would like to point out quadratics and smooth functions may fail to exhibit. Okay, so final step is actually, can we solve this with an equation? And by now you have figured out that actually I've been just repeating the same arguments over and over. And essentially you compare two gauge functions, which means the sets have to be equal. And that essentially gives you a fixed point set equation. And when essentially it tells you very much the same, that actually, because you compare the gauge of this minimum, which is gauge of Sx, to actually you equate it to gauge of P of X, S has to be equal to P. So Minkowski function, in order to verify this, set S and P have to be equal. This will exist if A is strictly stable, if B is strictly stabilizable for a fixed property set C. And now this is an important point that actually, and this is perhaps the technically most challenging result, is that actually solution is unique in this case. Now let me explain why this is very challenging. In the initial attempt to prove this result, I had to resort to something which is known as a Blaschke selection theorem. And now Blaschke selection theorem tells you that actually if you take a sequence, bounded sequence of convex sets, then you can extract convergent subsequence. And of course, with certain monotonicity, then original sequence would be that subsequence. And that gives you existence of the limit. And then actually you needed to use stability properties to actually establish the uniqueness. Now, of course, one can argue that you can actually resort to the Blackwell's argument that actually when you have certain contractivity of Bellman operator, you have a unique solution to the Bellman equation. Well, I mean, proving contractivity of these operators is not so simple. So in order to set it up in order that actually you have a contractivity, you need to do a lot of heavy lifting. So the way this was proven initially was through Blaschke selection theorem and stability arguments, but actually in the most recent work, I proved it using Tarski fixed point theorem, where I actually showed that certain sets, there is a uniform upper bound on this operator, and then actually you have a certain set which is a complete lattice, and then actually you can call upon the and the operator is monotone on this complete lattice, so you can invoke the Tarski fixed point theory, which tells you that set of fixed points is a complete lattice itself. And that's the first argument that gives you existence of the fixed point. And then the second step, which was the most difficult for me at least, was to show that actually this set of fixed point is actually a singleton. So that actually upper and lower fixed points coincide. And that gives you the argument. The argument is in the paper, which is under review. So it's really, really technical argument. Now, again, to say polyhedral structure is preserved, that's repeated. And one can actually handle the robust case. So you can do min-max problem and you can get the same result because, again, I said, essentially, it's just redefining the operator. And actually, everything comes very nicely because you preserve the properties of Minkowski functions through the maximization and through parametric verification. Now, let me give you one example, which actually points out how actually, even though one thinks that there is a nice structure that you're dealing with convex problems, that actually continuity, this fails to be true in general. And an example for trivial dynamics, say 0 and base 0, if you take P to be actually the Euclidean norm B22, so that just essentially this set, as I'm showing, you have the boundary and set. And if you take this interval from -1, 1 in the third coordinate, and if you actually take a convex hull of that, what you see then actually when you project this, the optimal value function would be essentially Euclidean norm ball 2, but actually optimizer would jump at this point. So essentially that tells you that actually there is no hope in general setting with this even though the sets are proper C sets and they're nice, convex, compact, there is a still possibility for optimizer to be set valued function. Now, this is an example that actually came from discussion with Professor Zwianstein. And now to give you a few examples in one dimension where you can visualize this simply, if you take a scalar system A equals 1, B equals 1, and if you take the set P to be -1, 1, that's going to be a fixed point. Set C is infinity norm ball in 2, then actually you can get a set R of this form. And if you look at the projection, that projects down to P. And if you want to find the optimizer, well, essentially you see that it's this line. So in this particular case, it's a single valued. Of course, everything has to do with what happens with the vertical points or vertical, so to speak, vertical supporting hyperplanes to the set. And when actually you have multiple points at which these hyperplanes are supported, you get multi-valued optimizers. And this is another example. All what you do, you just change the cost in XU space, and you see that it's a multi-valued. Now, but what you see actually, because this is polyhedral case, as I was making remarks, the structure is polyhedral. The set valued map is obviously the graph is the union of two very simple polytopes. And actually you can see that this is Lipschitz continuous as well. So this is a nice illustration. And now just to give you an illustration, when you iterate this on a more interesting shapes, like the shapes which are combined from the, okay, so this set Q is a stage cost. It's obtained, so C is obtained through this operation, R is -1, 1, and Q is given as a kind of combination of the two infinity and 1 norms. Now, this is very interesting because in many problems, you may want to deviate from the standard, from any of the standard norms, and you may generate more exotic norms because they may give you better properties in certain directions of the space, which might be of interest. And what you see that the gauge is, this gauge is essentially fails to be differentiable at these points, but that doesn't matter because we propagate the generators P1, P2, P3, P4, P5, P6. This gives you the value functions. And essentially, if you think about it, the convergence of generator sets gives you convergence of the value functions. And in this particular example, the value function is it has a very interesting form. I mean, it's a piecewise convex, and the optimizer is piecewise linear. It's defined in a few cones. And well, that brings me to a conclusion. I hope, yeah, just about in time. I think essentially, in a way, I mean, I've given this talk several times, and I think I never do it the way I want to do it. I think there is way too much material, so I have to apologize for that, but it is what it is. I try to communicate ideas which you can find in my papers, which I believe are very interesting because they provide definitely very interesting insights into another class of approaches to stabilization and optimal control synthesis. And you know, in 2008, Rudolf Kallmann's plenary talk at IFAC contained an interesting remark by Rudolf Kallmann, which essentially said that further advances in control will happen when element A becomes a standard in control. Now, of course, by now, this has become a standard. And in fact, set value analysis and calculus for control has been available since the 1960s, since early work of Einstein, Oman, Oban, Frankowska, and numerous people. And of course, there is a fantastic work in terms of summarizing this within the mathematical concepts of variation analysis by Professor Terry Rockefeller. It's a brilliant book with a lot of useful results and insights. And what one can observe that actually over the last 20 years, there has been definitely increased popularity in contemporary controlling applications. And I would like actually to add a very important point here. The reinforcement learning techniques have started kind of in a kind of an ad hoc manner. So the people have been trying to develop a lot of notions which actually already existed in control. So very typically, when you talk about safety that actually people introduce from, well, coming from computer science background, that was typically a notion of invariance that actually we considered. So somehow there were notions that kind of were developed in a parallel in two different folds, though they might have existed in certain communities prior to the other communities, but used in different manners. In either case, what I'm trying to say is that these notions are really conceptually powerful and they're topologically flexible, but still, nevertheless, they do offer non-trivial computational issues and challenges. And to my big surprise, over these few years that I developed a number of these results, actually, they might seem simple, they might seem, I don't know, I mean, it's difficult to quantify them now. Once everything is simple once you do it. And I like to think that some of these are very elegant because they actually are very simple to explain and they follow from very basic principles in convex geometry. But I couldn't find them published, actually. That was a kind of very big surprise to me. And with this, I'll close what I have to say, and I'll be happy to take any questions you might have.
Well, thank you very much for the
question. It's 3 parts.
Sure.
But before we go into the questions, let me thank Sasha for an amazing talk. So congratulations.
I don't know if it's amazing. Maybe it's a talk.
It was very, very insightful. We really enjoyed all the connections.
All right. Well, thanks. Thanks. I hope it has some links between different notions and concepts. Thank you.
So now, yeah, we can take questions now.
Yeah, that was my first remark, actually, that this is really very beautiful stuff.
Thank you.
Very insightful and very mathematically pleasing.
Thank you.
Want to ask a sanity question on my own part, see if I understand this stuff, is that essentially this involves constructing piecewise convex surfaces in Rn on a computer if you're actually going to use it. Is that correct?
Well, okay, so this is an excellent question. So this question touches upon what does it mean to compute a set.
Yeah.
And this is a kind of, you know, it is about the same question is what does it mean to compute a function?
Yeah.
You know, there are two things we want to separate. One of the things is actually representation of the function, and the second thing is evaluation of the function at given points. And this is important, and actually this is something which in more recent work, in some of the work which actually I listed, I differentiate between explicit and implicit representations. Now, explicit representations would be finding closed loop form, functions which represent the object. And this may be very complicated because, you know, try to think about representing intersection of 100 ellipses. That's amazingly complicated, but it's not necessary, because essentially if I want to compute the maximum of intersection, I can just compare 100 numbers, and that's very easy. But then that's an implicit representation. So essentially I might have a problem to plot the set, but I might have a representation which is very easy to use for something else. So I think this question comes to really tailoring the representation of the object for the purpose that actually you have in mind to use it for.
Okay.
I don't know if that answer, does that answer? So
you answered that. I think I sort of know what you're doing. Okay.
So essentially, okay, let me try to be a bit more specific. So what I would advocate in that case is that actually you either keep it in a, so I would seldom advise that you compute the closed form of this expression, closed forms of this set. I would advise that actually you use the rules of Minkowski and support functions to express these objects in terms of sums of certain functions which you can easily evaluate.
Thank you. Very good. Okay. Now I come to the final thing that I was leading up to. You have made the assertion that you need AB to be strictly stabilizable. I'm really interested in the problem of what if it's merely stabilizable? Can you make connections with simple boundedness?
Yeah, so that's precisely what one would need to do with. Okay, so there are two things. So when you take only stabilizable, then actually issues arises. We need to talk about possibility that we lose uniqueness of the solution. That's number one.
Yeah.
So then we need to put some further conditions on the set that we use and the matrices to have. So typically, when in a quadratic case, we have conditions which are in the form of detectability. So we would have to mimic this, but now this is a bit more complicated because the functions we deal with are just convex functions. They don't have a nice representation. So we have to have a kind of more general notion of the conditions used in LQR, and that would go through. But essentially, the question then also arises how numerically convenient such conditions would be. So I don't see it as a big problem. I think it's doable, but it requires careful analysis and tedious algebra.
Yeah. Okay, thank you.
Okay. Thank you, Sajid and Don. Any other questions from anybody else?
I can ask one. So the approach you presented was for discrete dynamical systems. Is there a similar approach for continuous time systems?
Well, I mean, there are certainly some works on looking at the Minkowski on utilizing the Minkowski functions for stability analysis in continuous time. In fact, I think even Rafael Gobel has looked at something, not necessarily in the framework I've done, and there are other people certainly. I'm not so sure how complete it is, and I personally have looked at one specific instant. It gets a bit more involved in terms that actually the calculus of continuous time problems and discrete time problems is slightly different. So it becomes a bit more technical. So publishing it out in automatic in IEEE, even though it's a bad reason to do research to publish in these journals, may be very hard if you have such a technical aspect. So you would have to go for a kind of SIAM type of publication. So I think it's doable. No, I think actually I know certain things are doable in continuous time, but they're considerably more technical.
Yeah, you're going to get into measure theory. That's the problem.
It becomes very complicated because you lose non-smoothness. And now when you propagate this in continuous time, you have to regularize the solution. So it's a lot of things you need to worry about, actually.
One more question. For the optimal case, can you clarify how you're specifying what the cost function is? Is that what the set C does?
So do you want me to go to the formulation, or do you want me to go to the example to explain what's
maybe the example would be more helpful.
Okay. So in this specific instance, let's say it's a scalar. So your cost C, okay, let me start with the first one. This is a simpler one. So the C is essentially just infinity norm ball in a XU space. So it's -1 times -1. So it's interval -1 squared, yeah?
Yeah.
So it's just essentially infinity norm ball. Now, essentially, this tells you you penalize the XU, infinity norm of XU. Okay. Now, in the other one, you have a -2 times -1 So this is just polyhedral set. So this is not necessarily norm. It's just Minkowski function of a polyhedral set. In the third example, it's a bit more complicated because in XU, you have -1 and in a so in the first, because now we have a system which has 2 states and 1 control. Okay, so the Q penalizes the states. So this is the way you penalize the states. So you can penalize, for example, in the first quadrant, you can think of this as a penalizing infinity norm. In the second and the fourth quadrant, you penalize 2 norm, and in the third quadrant, you penalize 1 norm. But of course, then you have to mix those two to get a set C, and that gives you the formula for the set C when you have these expressions. So this allows you to actually, effectively, you can draw almost any convex set and you can use that. Now, the only requirement for a proper C set is that this set is compact. Of course, convex, compact, and it contains origin in the interior. Okay? And now, if the set is symmetric, then it's a vector norm. In more general formulation, that's what I said here. Okay, so Minkowski stage function, L of XU, is a Minkowski function of a proper C set in Rn plus M. But with the examples, I'm just simulating, you can actually do the classical, in classical control, in classical LQR, you have X transpose Q, X plus U transpose RU. But this is, you can rewrite this in terms of XU times some other matrix. Yeah? And you can do the same with this. You can do the same with the Minkowski functions, and this is the formula here. So I think in one of the papers I did even give this formula how to convert if you have a separate cost to the joint cost. Does that answer? Was that the question, or did I miss it?
Yeah, that helps clarify it. Thank you.
All right.
Thank you. Any other questions, anybody? All right. Well, again, thank you so much for presenting. Again, it's very late, I know, where you are. We are excited to learn about all these results, and there are, I think, a lot of interesting connections to some of the things we are doing, and maybe we can pursue some of those. Thanks everybody else for attending, and we'll see you in a couple of weeks for our next seminar.
Okay.
Thank you, Eric, for setting it up.